Hi everyone. This is the first of probably what will turn out to be several PowerPoint videos on the different hypothesis tests that we're going to be conducting this semester. The focus of this one is a hypothesis I'll call the Z-test for the population mean. And just a little review, as I've done in other videos. A hypothesis Z-test for a population mean is based on the normality, as what we've done with confidence intervals as well. It's based on the normality of the sampling distribution of the mean. Therefore, before you or after you conduct the test, you've got to make sure that it's valid, and that's the validity conditions. There must be a random sample of size n drawn from the population, sample size greater than 30, or the population is known to be normally distributed, and the standard deviation of the population is known. As we'll find later in the semester, you rarely know the standard deviation of the population, but for now we'll assume that it's known. If these conditions are met, then some things we know about the sampling distribution is that its mean is equal to the mean of the population. The standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of n, and it's approximately normal. Because it's normal, we can determine probabilities associated with different sample means. Okay, so here's the logic of the hypothesis test. First of all, it's a hypothesis test, any hypothesis test, but the hypothesis Z-test is about competing claims about the population mean. So there's two claims. The null hypothesis, H sub naught, is that the mean of the population equals some value, I'll call it V, versus the alternative hypothesis, which is either the mean of the population is greater than V, the mean is less than V, or the mean is not equal to V. In this video, I'm going to focus on the fact that on the alternative, rather, that the mean is greater than V. Values for less than V are similar for tests where the mean is not equal to V are slightly different, and we'll look at those in a separate video. So the process is you select a sample. Okay, we're going to assess these claims. Select a sample and calculate the sample mean. Assuming that the null hypothesis is true, what we want to do is determine the likelihood of obtaining that sample mean, or something even more extreme. In other words, something that is even more consistent with the alternative. So if our alternative is that the mean is greater than some value, in other words, here's V, we hypothesize that the mean is greater than V. So sample means that are consistent with the alternative would be values that are significantly greater than whatever sample mean we get. So this might be our sample mean that's bigger than V, or one up here, or one up here, or one up here. In other words, you can go farther and farther away. All of those would be more consistent with the alternative. So we determine the likelihood of finding a particular sample mean, the one we get from the sample, or something even more extreme, and that likelihood is called the p-value. Then you have what's called the decision rule, which states that if this p-value is less than some stated level of significance, you reject H0 and accept HA. In other words, if the sample mean is somewhat rare, we're going to say, well, this assumption that H0 is true cannot be true, and therefore we accept the alternative. If the sample mean is not rare, and the level of significance is the level of what we consider to be rare, typically 5%, then do not reject H0. In other words, we'd have no evidence that the mean is bigger than V. Okay, to find this p-value, what we're going to do is we're going to use what we know about the sampling distribution of the mean. Okay, so if the validity conditions are true, or met rather, and H0 is true, then we know that the sampling distribution is normal. We know that the mean of the sampling distribution is V, and the standard deviation is the standard deviation of the population divided by the square root of n. Using this, we can find the z-score of the sample mean we calculated. Okay, that z-score would be the sample mean minus its mean, which is V, over over the standard deviation of the sample mean, and we call that the test statistic. So when I say what's the test statistic is the value that would allow you to determine the likelihood of your sample mean. Okay, then we simply go to the normal table or to a stats package, I'll do both in this video, to determine the probability of obtaining the observed z-score or something even more extreme. All right, let's look at a particular example. Okay, this is from insurance. Insurance companies have to set their rates on second vehicles. They have primary and secondary vehicles, assuming second vehicles are driven a particular mileage. So let's say that a particular company, its second vehicles assume that cars are driven an average of 12,000 miles. If cars are actually driven more than 12,000 miles, the company should be charging higher rates because there's increased risk with additional miles. Okay, to determine whether second cars are driven an average of 12,000 miles or whether this figure is higher, which would mean that we should be, again, charging additional premiums, the company randomly selects 36 cars and monitors how far each is driven over a 1-year period. For these 36 cars, the mean number of miles driven is 12,315 miles. So this is the sample mean. Assume that the company knows that the standard deviation of miles driven by all cars, all second cars I should say, is 1,300 miles. And use alpha, alpha is your level of significance, as 0.05. Okay, so the competing claims, the null hypothesis is that the mean number of miles driven by all second cars is 12,000 versus the alternative that the mean is greater than 12,000. The alternative also often comes from the clues here. The car company wants to determine if, here it is, to determine whether second cars are driven an average of 12,000 miles or whether this figure is higher, greater than 12,000. The decision rule, which is going to be the same for essentially all hypothesis tests, we're going to reject H0, accept HA, if the p-value is less than our level of significance, which is 0.05. Okay, since the random sample of 36 cars was selected, the number of cars selected is 36, right, is greater than 30, and the standard deviation of miles driven by all second cars is known. The sampling distribution of the mean is known to be approximately normal. In other words, the validity conditions are met. In every test, you need to state or at least address the validity conditions to essentially determine that you can actually conduct the test. Okay, so we received a sample mean of 12,315 miles. If the null hypothesis is true, the mean of the sample mean, so this is the sampling distribution, the normal sampling distribution, its mean would be the mean of the population, which if null hypothesis is true, is 12,000 miles. Okay, so we would determine the z-value of this sample mean, and then we determine the p-value, which is the probability that we have a sample mean mileage for the 36 cars of 12,315 or even more. Again, even more because we're looking for evidence that the mean of the population, that the number of miles driven by all second cars on average is greater than 12,000. So being more extreme would be values that are 12,315 or even more, because those would be consistent with the alternative hypothesis. Okay, for the calculations, to find the p-value we use the test statistic. So that would be the sample mean minus what we hypothesize the mean of the population to be, 12,000, divided by the standard deviation of the sampling distribution, equals 1.45. Again, 1.45 makes sense. This is greater than the mean, so we have a positive z-score. So this is about 1.5 standard deviations larger than the mean. From the z-table, and again, the z-table always gives you the probability of falling between the mean and the score. So that is 0.4265, but we don't want that value. We want the probability of being greater than a z-score of 1.45, so we'd subtract from 0.5, and that gives us a p-value of 0.5 minus 0.4265, or 0.0735. In other words, about 7.35%. Interpreting that value, that says that we have about, excuse me, a 7.35% chance of finding a sample mean of 12,315 or more if the null hypothesis is true. It's somewhat of a low probability, but it's still within the realm of possibilities. Okay, but getting back to our decision rule, we said that we're going to reject the null hypothesis when we find an outcome that has less than a 5% chance of happening. Since this p-value is not less than 0.05, okay, which is a level of significance, do not reject H0. So the conclusion would be that there's no evidence based upon this sample that all second cars are driven more than 12,000 miles on average. For your test, for the test that you conduct, what I'd like you to do is clearly state the hypotheses, give me the decision rule, give me the test statistic, how you would calculate this probability. Even if you do it with StatCrunch, I still want to know how you would calculate this probability. In essence, this tells me which test am I conducting, and am I conducting the right test. Okay, show me the calculations, and then give me a nice clear conclusion. Okay, I'm going to do one additional test, and we're going to focus on something from StatCrunch, doing it with StatCrunch rather, which as you get into more and more complex tests are basically it's necessary with the amount of data to use a stat package to conduct the test. So this is based upon an example we've seen before in the confidence interval video. A school district uses reading recovery to remediate low-performing readers. The data contained in a file that I'll pull up in a second represents independent reading scores at 3 points in time before using reading recovery, at the end of 10 weeks, or for non-reading recovery students at mid-year, and then at the end of the school year. Okay, so the question the school district has, they're trying to assess reading recovery. Does the mean growth of all students in this school district using reading recovery exceed the mean growth of comparable students that did not use reading recovery? Okay, so I'm going to go to StatCrunch. Some things we need. So here's our data. We need to know, well, what are those values? What is the mean growth of all students who do not use reading recovery? Let's go to Stat, do a summary statistics on particular columns. We're going to find reading recovery growth, because that will give us our sample mean. Those are the students that we're interested in. And then the mid-year minus entry for non-reading recovery. This will be the statistics for essentially non-reading recovery students. To select multiple columns, you have to click Control. There we go. Compute, and we have some values that are calculated. This gives us the sample means for the 278 non-reading recovery students, the 537 reading recovery students. The standard deviation, we're going to make an assumption, as I'll explain in just a bit, that the standard deviation for the non-reading recovery students is equal to the standard deviation of reading scores for all students. Okay, let's get back to the PowerPoint. Okay, using these summary statistics, I have calculated these values from basically from the reading recovery and non-reading recovery students. We're going to use 4.21 as the standard deviation of growth scores for all reading students. Notice that the non-reading recovery students had an average growth of 7.75, so that leads to the hypothesis. The null hypothesis that the average reading score for all reading recovery students is equal to this, 7.76 when you round up, versus is it greater? Do we think that reading recovery helps students grow at a larger rate than those who don't use reading recovery? Okay. To conduct the test, what I'm going to do is go under Stat. It is a Z statistic. We have one sample. We're just going to be examining the reading recovery students. Now, we have the data, so I'll put that in. We're going to select the reading recovery growth scores. The standard deviation of the population I'll put in here is 4.21. The hypotheses are that the mean reading recovery score growth score is 7.75, 7.76 versus that the mean reading recovery score, growth score, is greater than 7.76. In this menu right here, you can select either of the three alternative hypotheses. Okay, compute, and you get some values, and I'll pull back the PowerPoint to show you those. Here are the values you get from StatCrunch. It lists the hypotheses. It says in your reading recovery we had 537 students. The sample mean growth score for those 537 was 11.69. Okay, and I'll sort of show you that visually. If the null hypothesis is true, the growth scores for all reading recovery students is 7.76. We found a sample mean of 11.69. Okay, the p-value is, how likely is that sample mean, assuming that the true average score is, the growth score is 7.76. How likely is the sample mean? In general, the p-score is always how likely is the sample value. Okay, a sample mean of 11.69 is about 21, a z-score of 21, so about 21 standard deviations greater than the true mean. Okay, if this is the true mean. The standard error is actually the standard deviation of the sampling distribution. Okay, the p-value is less than 0.0001, so to 4 decimal places it's about, it's basically less than 0.0001. So since this p-value is less than 0.05, which is the standard level of significance, we're going to reject H0. So we reject H0, we can conclude that the mean growth score for all reading recovery students is truly greater than 7.76. So in other words, using reading recovery results in greater growth than comparable students who do not use reading recovery.